Alright, so this video is going to be on how to analyze piecewise functions and find all those different characteristics of functions that we've talked about before. So what I've done is I've made the notes a similar layout to your worksheet, and then on the worksheet it gives you a picture of the piecewise so you don't have to graph it today, and then you're just going to analyze that based on all the things that I ask you to find. So first we have a cubic and a parabola, and the parabola is really not even, the parabola you can see the majority of. The cubic isn't really even a cubic, it's literally just a dot, which is why you're not seeing a cubic on the sheet. So this one, it hardly gives you anything. But what we'll go ahead and do is we'll start finding all of these things. So for part A, it asks you to evaluate the function at -5 and at +3. So if I evaluate the function at -5, then I have to consider which piece I'm allowed to use. So the top piece says to use the quadratic if the x value is not 3. The bottom piece says to use the cubic if the x value is 3. So since the x value is not 3, I'm going to use this one. -5 minus 3 is -8, and -8 squared is +64. Next, we're evaluating the function at 3, and so 3 minus 2 is 1, 1 cubed is 1. And with this one, with the -5, we wouldn't be able to evaluate that using the graph because -5 is off. The x value of -5 has a y value that's off the grid that we have. However, a x value of 3, we would be able to look at the graph and see that that's a y value of 1. So we could do that. All right, part B says to find the intercepts. So here I can't see where it crosses the y-axis, so that means I need to plug in 0 to find the y-intercept. But as far as finding the x-intercept, I can actually see that there are none, because on the x-axis there's a hole right there. So I'm going to say x-intercept none, and then y-intercept I'm going to have to plug in 0. So if I plug in 0, I get 0 minus 3, which is -3. -3 squared is 9, so the y-intercept is 9. Part C wants to know the domain and the range. So the domain, I can see that the parabola has everything except for 3. And then the cubic has 3, and so no numbers are excluded, so our domain is from -infinity to +infinity. The range is from down to up, and so I can see that the lowest value I have for y is 0, but I don't include it because it's a hole. And then my graph goes up forever and it doesn't skip anything else. So I'm going to say from 0 to infinity. All right, for D, we're looking for absolute maximums and minimums, and it looks like the absolute minimum of the graph is right here, but it's a hole, so it doesn't count. And we don't have any absolute maximums because we have the arrows going up forever, so I'm going to say none. No absolute minimums, no absolute maximums. E is the increasing and decreasing intervals, and so I can see that right here the graph is decreasing until it gets down to that hole right there, and then it turns around and it starts increasing. And so I'll go ahead and I'll label my x values. That's an x value of 3. So my graph is decreasing from -infinity to 3, and it's increasing from 3 to infinity. All right, F, determine if the function is even, odd, or neither. So if you guys remember, the symmetry is kind of helpful here. We could go ahead and plug in the x's if we want to see if it's even, odd, or neither. I would say that to check even and odd, you can kind of do step F and step G at the same time. So just remember that even graphs are symmetric over the y-axis, right? We had our example of an even graph was a parabola. This is symmetric to the y-axis. And then odd graphs are symmetric to the origin. And so if we check the symmetry, then we'll actually know the answer. So we can kind of do F and G at the same time. So if I look at this graph, it is not symmetric to the y-axis. I couldn't fold the paper over on the y-axis and have the same thing on each side. Symmetry to the origin means I can put my pen in the middle of the origin and spin it around and it looks the same. That's definitely not true. So for F, I'm going to say neither. Now, for part F and for part G, for even, odd, neither, and then for symmetry, you're going to find that oftentimes there's nothing there for piecewise functions because they don't often have a lot of symmetry, but it's worth it to check anyway. So we said that there was no symmetry to the y-axis, no symmetry to the origin. There generally shouldn't be symmetry to the x-axis because that would mean it's not a function, and these are piecewise functions. So the only case where it would be symmetric to the x-axis is if your line went across the x-axis. So we're going to say it has no symmetry. Discontinuities, your piecewise functions should have lots and lots of discontinuities as you're going through this assignment. Not like each assignment problem should have 5, but like pretty much every problem is going to have at least 1. So I'm going to say that we have a discontinuity at x equals 3, and it's removable. So I'm going to write removable discontinuity at x equals 3. You'll notice when I write removable, half the time I put the E in there and half the time I don't because I don't know how it's spelled. So don't judge me, but if you figure it out, let me know. Removable discontinuity at x equals 3. Describe the boundedness. So this graph is bounded below because it doesn't go below a certain point. It is not just bounded in general because it does go up forever. So that's why we don't say that. All right, and then J, our end behavior. So I'm going to say as x approaches negative infinity, or as I look to the left of the graph itself is going up. So f of x approaches infinity. As x approaches infinity, as x goes to the right, the graph also goes up. So as we look to the left, it goes up. As we look to the right, it goes up. And so those are all the things that you're going to be finding for each of your functions. Okay, let's try the next one. So here, maybe I'll zoom in, see if that helps. Okay. So same things again. So we're going to evaluate the function for -5. And here we have a little bit more thinking to do as far as knowing where we can plug the number in. So -5 is not greater than 1. I cannot plug it in there. -5 is not between -3 and 1, so I can't plug it in there. -5 is less than -3, and so this is where I plug it in. And here, if you look, there's no x value to plug it into, so that means at -5, your value is -6. There's nothing to plug it into, so we just take that number. And if you wanted to check the graph for that, then you could look at an x value of -5, you have a y value of -6, right down here. All right, f of 3, we're going to plug into the bottom one because 3 is bigger than 1. And so 3 plus 3 is 6. And again, we could look at the graph for that one. X value of 3 has a y value of 6. For B, we're looking for our x-intercepts and y-intercepts. So for the x-axis, it never crosses, so we're going to say none. For the y-axis, it looks like it crosses at -1. So this time, we didn't have to plug in 0. We could just look at the graph. If you wanted to plug in 0, you could. And so 0 would be in between -3 and 1. And that's why it has a y-coordinate of -1. Go back to A. I wrote f of something, but this is a g of x equation, so we got to fix that. My bad. Okay. So x-intercept, y-intercept, we're done with that. Now we're going to look for our domain and range. So for the domain, this one says everything less than -3. Then this one says to include 3 and do everything between -3 and 1. And then this one says to include 1 and use everything bigger. So if you paid attention to that, there was nothing excluded. It looked like maybe -3 was excluded, but it wasn't. It looked like maybe 1 was excluded, but it wasn't. So we're going to say -infinity to +infinity. You're going to find a pattern on the worksheet that I made for you that often the domain is negative infinity to positive infinity. That's not because piecewise functions always have that. It's because the worksheet generator that I used likes to put arrows on either side and make them go forever. So some piecewise functions would kind of like stop it right here. They'd be like, nope, doesn't keep going, it stops. So just keep that in mind. For the range, this range is kind of interesting. We're going to say we have a y value of -6, and we have a y value of -1, and then we have y values from 4 and above that. So I'm going to say we have a y value of -6, we have a y value of -1, and then we have y values from 4 and above that. So I'm going to say 4 to infinity. And I put brackets around all of these because you can find y coordinates where there's a value of -6, and you can find points that have a y coordinate of -1, and there's a point with a y coordinate of 4. So all those numbers are actually used. All right, for D, we're looking for absolute minimums and maximums. The very lowest point on the graph, this is kind of an interesting one because the very lowest part right here is an entire function. And I honestly don't know if that would, if any of those points would be considered minimums or not. I don't think you can have a whole range of numbers for minimums, absolute minimums. I'm not going to give you one like that on a test. I wouldn't give you one where you are not quite sure. So we're going to say none just because I think it has to be one point. I don't think it can be all the points like that. But that would be something that as your teacher I need to look into. All right. Next, we're going to look for increasing and decreasing intervals. And there was one I did not put on there, and that's a constant interval. So I'll have to fix that for your assignment. But we can go ahead and find it in the notes. What I mean by constant is that's an interval where, as you can see, it stays flat. It doesn't go up, it doesn't go down, it stays flat. So here we're going to say we have a constant interval, C-O-N, from -infinity to -3. And then we have another constant interval from -3 to 1. And then this one right here goes up. So we would say it's increasing from 1 to infinity. So constant interval from -infinity to -3, -3 to 1, and then increasing from 1 to infinity. All right. Checking for even and odd and symmetry. As you can see, you can't fold the graph over the y-axis. You can't fold the graph over the x-axis. If I put my pencil right in the middle and spin it, that is not the same picture as it was when it was like this. And so that means that it is not even or odd, and there is no symmetry. All right, we definitely do have discontinuities. So there's one jump discontinuity at -3. There's another jump discontinuity at +1. So I know that these are holes, but we don't call it a removable discontinuity unless it's a hole that is got stuff on either side. If it's a hole like this, then that means it's usually a jump. So we're going to say that this is a jump discontinuity. So jump discontinuity at x equals -3 and x equals 1. Describe the boundedness. So here we're going to say that this one is bound from below because there is a point where you don't go any lower than that, but this is not bound from above because it does go up. So I'm going to say bounded below. And then J was describe the end behavior. So I'm going to say that as x goes left forever, the y value doesn't go up and it doesn't go down. The y value stays at -6. So we're going to say as x goes left forever, the function goes to -6. So as we look to the left, the function goes to -6. As we look to the right, the function goes up. Now with the -6, you might be confused because I did write a negative infinity right there. But that negative infinity matches this negative infinity. It was me talking about left and right. It was not me talking about up and down. So that's why we say as x goes to the left, the y value goes to -6. So be careful of that. I know that that can be easy to kind of mix up. Okay. I'm going to do one more example and then we're going to leave the last one for class to go over. So first we're going to evaluate the function for -5 and 3. So we want to plug -5 in where we can see that it's part of the domain for that little piece. And so -5 is less than -4. And so -5 plus 5 is 0. 0 squared is 0. So that happens to be one of the x-intercepts actually. And we can see it right there. There's the x-intercept. And then f of 3, we cannot plug it in here. We can plug it into this one. So that's the square root of 3 minus 1. And I'm going to call that square root 2 and not get my calculator out. So those are my two values right there. But I should be able to see that at 3, I'm going to have a decimal answer, which makes sense since I had square root 2. All right, for part B, we have x and y intercepts. We already found the x-intercept. That was -5, 0. The y-intercept is at 6. Or if you wanted to plug 0 into the function, you could. I think domain and range is next. All right. So domain, we have everything less than -4, including -4. Then everything from -4 to 2, and then everything bigger than 2, and so that means our domain is all real numbers. For the range, we're going to look how far down the graph goes. The graph goes down to 0, and it includes 0. And then I don't even have to look at these other pieces. I can see that the range is going to use all these y values, and it goes up forever. So I'm just going to say 0 to infinity. For D, that was absolute maximums and absolute minimums. We do not have an absolute maximum because this graph does go up forever, but we do have an absolute minimum. It was that same x-intercept right there. So the absolute minimum is the point -5, 0. All right, increasing, decreasing. So this one's kind of a complicated graph. So to make it easier for myself, I'm just going to go through and label each piece. So this is an x value of -infinity, and I can see that my graph is decreasing. Then I hit an x value of -5, and my graph increases for just a very short period, and it increases until -4. Then from -4 over to +2, the graph is constant. And from +2 to infinity, I can see the graph is increasing. So I'll go ahead and write these down. My increasing interval was from -5 to -4, and from 2 to infinity. And remember, when I do increasing, decreasing, and constant, I do not use brackets. I've seen it done, but it's not very common. Yep, that was the only decreasing one. And then we only have one constant, -4 to 2. Okay. All right. F and G was the symmetry. So we'll checking for even and odd and checking symmetry. So I can see that this graph is not even or odd. It is not, it doesn't have any sort of symmetry. So next we're going to look at our discontinuities. So I have a jump discontinuity right here and a jump discontinuity right here. With piecewise functions, your most common type of discontinuity is going to be jump, and sometimes hold, but mostly jump. So if you feel like that answer is coming up a lot, that's okay. You're doing it right. It is possible for a piecewise to be continuous, but not many of them are. And as far as infinite discontinuities, we could have it. You probably won't. Infinite discontinuities happen with rational functions. That's the ones that are written as a fraction. And we're studying those more next unit, which means we haven't done them yet. All right. Next, we're going to look at the boundedness of this function. It goes up forever, so it can't be bounded above. But it does have a low point, and so this one is bounded below. And then last, we want to do the end behavior. So as we look to the very left side of the graph, as x goes left forever, the y-coordinate is going up. And as we look to the right side of the graph, the y value is also going up. So as x goes to positive infinity, f of x also goes to positive infinity.